Hi, my name is ldesu3. I am going to present a paper about skill squatting attacks on Amazon Alexa. This paper focuses on the usage of speech recognition systems, their shortcomings, and how the attackers can exploit the misinterpretations of the voice interactions by these systems. First of all, I would like to acknowledge the original authors of this paper, Deepak Kumar, Ricardo Pacanella, Paul Murley, Eric Hennenford, Joshua Mason, Adam Bates, and Michael Bailey from the University of Illinois. This paper was originally presented at the 27th Usenix Security Symposium in 2018. The original link for the presentation is provided here. This is an overview of this presentation. We start with an introduction to voice recognition systems, a little background about how the Amazon Alexa works, the interpretation errors made by Alexa, followed by the problem statement on which this research work is focused. Then we will move on to the methodology carried out in this work, which explains the data source used to query Alexa and analyzing the various errors made by Alexa in interpreting the voice inputs. After that, we will be moving on to skill squatting, spear skill squatting, limitations, and the countermeasures. Finally, providing the future works mentioned in this paper. The attractiveness of commercial IoT devices has sparked an interest in voice systems that perform everyday tasks. Smart speakers like Amazon Echo and Google Home use voice interfaces as their primary input source. In 2017, more than 30 million smart speakers were sold, all of which use voice as their primary control interface. This research is focused on Amazon Alexa, the speech recognition system that powers 70% of the smart speaker market. Amazon allows the development of third-party applications called skills that leverage Alexa voice services. Many companies are actively developing Alexa skills to provide easy access to their services through voice. For example, users can now request rides through the Lyft skill, as shown in figure, and conduct everyday banking transactions with American Express skill. The following diagram depicts the Alexa flow. The user first invokes the skill by saying the skill name or its associated invocation phrase like Alexa, ask Lyft for a ride. The user's request is then routed through Alexa cloud servers, which will then determine where to forward it based on the user input. The invoked skill then replies with the desired output, which is finally routed from Alexa back to the user, such as the nearest Lyft driver is. Can speech recognition systems like Alexa make errors? Yes, Alexa makes mistakes. In spite of the growing importance of speech recognition systems, little attention has been paid to their shortcomings. While the accuracy of these systems is improving, many users still experience frequent misinterpretations in everyday use. How does an Alexa choose a skill? For example, when a user asks Alexa to tell some cat facts, Alexa searches for a skill called cat facts in its skill server and finds a skill that matches the interpreted voice and finds a skill named cat facts and responds to the user. A group of cats is called a cloder. So far sounds good, but what could go wrong? An attacker can leverage predictable errors in Alexa to route users to skills that they didn't intend to go to. Looking at the same scenario again, regarding the cat facts, an attacker can build a skill named cat facts, which sounds similar to cat facts. The attacker also knows that Alexa prefers the word facts to facts. So this time, when a request comes from a cat facts, Alexa chooses a cat facts which is not the intended skill that the user would like to go to. Misinterpretation of simple service like cat facts might not harm users, But these kind of misinterpretations by Alexa can be threatening as these speech recognition systems are used to avail various services like banking as well. Now let's look at a scenario where a user wants to perform a banking service using Alexa. Amazon Alexa has a skill called AmEx for providing the American Express banking services. When a user asks Alexa, Alexa, ask Amex to pay $1,000 to John. It chooses the skill called Amex and it sends a response with a login page to carry out the transaction to the user's phone. Now an attacker who knows that Alexa prefers character representation of words than the full representation of words designs a skill called am-x, which is preferred by Alexa. The attacker can now push a phishing login page through this skill, which is similar to the bank's login page by which the user's credentials can be compromised. An attacker can leverage predictable errors in Alexa to route users to skills that they didn't intend to go to. This is the main problem which is focused in this research work. Moving on to the methodology carried out in this research, it mainly contains the following stages. Speech-to-text test harness for recording the transcripts of voice interpretations by Alexa. Speech corpora, the data source for voice recordings. Querying Alexa with the data source. Analysis of Alexa interpretations of these input voice recordings to measure its accuracy. Quantifying the frequency of its interpretation errors, classifying these errors, and explain why such errors occur. The paper later focuses on investigating how an adversary can leverage these errors to cause harm to users in the Alexa ecosystem. To the end, the authors introduced a new attack called skill squatting and spear skill squatting, by which the attacker can target a single user or a group of users. Coming to the speech-to-text test harness, Alexa does not directly provide speech transcriptions of audio files. However, it does allow third-party skills to receive literal transcriptions of speech as a developer API feature. In order to use Alexa as a transcription service, the authors built in an Alexa skill called Record This that records the raw transcript of input speech. This is the architecture of the speech-to-text harness. As you can see, the client sends a speech sample of word apple. Alexa transcribes it for the skill server, which then returns the transcription as a reply to Alexa and back to the client. In order to study interpretation errors in Alexa, the authors used two externally collected speech corpora. A full breakdown of these datasets is provided here. 6 dialect regions define broad classes of speech patterns in the United States, which are used to segment nationwide speech project dataset. The NSP dataset is used as the primary source for speech samples, which contains 188 words from 60 different speakers, making a sample of 11,460 words. The forward dataset is solely used for cross-validation, as more than 68% of the words in the dataset are only spoken by a single user. The authors then use the test harness to query Alexa for a transcription of each speech sample in the NSP dataset. They sent each speech sample to Alexa 50 times, which provided 573,000 transcriptions across the 60 speakers. Later on, an empirical analysis of these Alexa transcriptions is done to measure its accuracy, quantify the frequency of its interpretation errors, classify these errors, and explain why such errors occur. Alexa successfully interpreted only 394,750, which is 68.9% out of the 572,319 queries. It is also observed that the Alexa errors do not affect all words equally. The table here shows the best and worst interpretation accuracies for individual words. We find that the words with the lowest accuracy seem to be small, single-syllable words such as beam, calm, cold, etc. In investigating the distributions of misinterpretations per word, the authors observed that for each of the 188 words, there are 1 or 2 interpretations that Alexa outputs more frequently than the others. The graph represents the plotting of the error rate by the rate of the most common error, MCE, for all the words of the dataset. Points in the upper right quadrant represents words that are misinterpreted both frequently and consistently. In the given dataset of 188 words, 24 words, which is approximately 13%, fall in the upper right quadrant. Once these errors are classified, the authors identified 24 words for which Alexa consistently outputs one wrong interpretation. They next investigated why these systematic errors occur. They have segregated the same as shown. First, homophones. These are the words with the same pronunciation but different spellings. Example, sail, S-A-I-L to S-A-L-E, sail. Alexa misinterprets due to same pronunciation. Second, compound words. Alexa appears to break these into their constituent words rather than return the continuous compound word. For example, superhighway is split into 2 words of super and highway. Similarly, outdoors is split into out and doors. Third, phonetic confusion. Alexa often misunderstands certain specific phonemes within words while correctly interpreting the rest of them. Example, wet to what, where the phoneme EH in wet is confused as AH in what. The other errors. There are few errors where there is no auditory reason found why these interpretation errors occurred, even though in listening to each speech sample individually. This is the table that shows the list of various predictable errors. Then there arises a question. Can these predictable errors be used to route users to unintended skills? In this work, a new attack called skill squatting is introduced, which exploits predictable errors to secretly route users to a malicious Alexa skill. When a user attempts to access a desired skill using their voice, they are routed instead to the malicious skill due to a systematic error in the interpretation of the input. This attack is more similar in style to domain name typo squatting, where an attacker predicts a common typo in domain names and abuses it to hijack a request. The next thing is to validate skill squatting. The provided table shows the results of testing performed on 27 skill squatting attacks. The pairs of target and squatted skills are built using the squattable words of training set. The authors are able to successfully squat 25 skills, which contributes to 92.6% of the skills at least one time, demonstrating the feasibility of the attack. The authors then investigated on how these squattable words can be used to target existing skills in Alexa. Most of the words are interpreted as nouns. As shown in the table, 5 are cases where Alexa returns a proper noun that is a homophone with a spoken word. For example, main, M-A-I-N to main, M-A-I-N-E, boil, B-O-I-L to B-O-Y-L-E, boil, and outshine to O-U-T-S-H-Y-N-E, outshine. Acquiring the speech corpus may prove too costly and in some cases infeasible. So, the squatting attacks by an attacker can be extended further by amplifying the value of speech corpus by reasoning about Alexa misinterpretations at the phonetic level. Coming to algorithm, the authors developed an algorithm to find errors at phonetic level. The first step is to identify the input-output mapping of correct phonemes. Second, to inspect if any additional phonemes inserted into the output that do not correspond to a phoneme in the input. And finally, analyze the remaining unmatched phonemes of the input and map them. This table shows the examples of squatted skills in the Alexa skill store that drew the researchers' attention during manual analysis. Notably, a customer review of the fish gig skill noted that they were unable to use the application due to common confusion with PHISH fish gig to FISH fish gig skill. The next question asked in this work is, can an attacker use skill squatting to target specific groups of people? To accomplish this, the authors introduced a variant of the skill squatting attack called spear skill squatting. Spear skill squatting extends skill squatting attacks by leveraging words that are only squattable in targeted users' demographic. An attacker can leverage accent-specific predictable errors in Alexa to route distinct group of users to skills they didn't intend to go to. This is a six-way Venn diagram which depicts regional intersection of squattable words. The current blue block shows the distribution of predictable errors by region. Here the blue box shows how the predictable errors are distributed across different regions. If a line connects a couple of dots, it explains as all that regions exhibited the same group of errors. This graph space illustrates that 5 out of 6 regions there are predictable errors which are unique to that particular region. The provided table shows the spear skill squatting by region. 11 predictable errors are chosen that are specific to a particular region, which are then applied with an identical technique and tried to validate if the speakers of the same region have higher squat rate when compared to everybody else. 8 out of 11 errors are successfully squatted. In the same way, they applied the technique based on the gender pronunciation, and the current table shows spear skill squatting by gender. We will now move on to the major limitation in this work, which is obviously the dataset. Only 60 users with just 188 words are chosen. This is inadequate for measuring the full scale of systematic misinterpretations of Alexa. The other limitation is that this work is carried out in a developmental environment on the key assumption that triggering skills in a developmental environment works similarly to triggering publicly available skills. Moving on to the countermeasures, the skill squatting attack relies on an attacker registering squatted skills. In that case, all skills must go through a certification process before they are published. To prevent skill squatting, Amazon could add to the certification process both a word-based and a phoneme-based analysis of a new skills invocation name in order to determine whether it may be confused with the skills that are already registered. As a future work, a more diverse dataset can be used to more thoroughly investigate systematic errors and their security implications. It remains unclear how effective the attack would be in the wild. In order to observe this, the authors would need to submit public skills to Amazon for certification. If an attacker realizes that the users trust voice interfaces, More than any other forms of computation, they may build better, more targeted attacks on voice interfaces. The, technique, the techniques used to build these models will work as long as we can leverage a speech recognition system as a black box. Future work must be done in replicating our techniques to other speech recognition systems. In conclusion, we can say that the authors investigated the interpretation errors made by Alexa, then showed how an attacker can leverage systematic errors to secretly trigger malicious applications, along with how this attack could be extended to target users based on their demographic information. That's all for this presentation. Please feel free to post your queries under respective Piazza post. Thank you for giving me this opportunity.